AI paper slop. Today, we are unpacking InternVLA-A1.5, Unifying Understanding, Latent Foresight, and Action for Compositional Generalization by the Physical Intelligence team at the Shanghai AI Laboratory. So here is the reality of modern robotics right now. We basically keep giving our AI lobotomy.
I really do, yeah.
Because to teach a language model physical dynamics, researchers usually force it to generate video pixels from scratch, which, burns massive compute and basically destroys its semantic reasoning in the process.
Right, it overwrites the brain.
Exactly. But InternVLA-A1.5 fixes this. It builds on a Qwen 3.5 2B backbone that never actually stops its vision question answering training. So the core intelligence stays totally intact.
Which is huge.
And instead of generating those costly pixels, it uses a tiny set of learnable foresight tokens to query a frozen WAN 2.2 video model during training. So it extracts the physical dynamics purely in latent space.
Right.
And then it completely drops the massive video model at inference to allow for actual real-time robotic control.
And for anyone building these systems, that inference drop is the holy grail. You are capturing the physics intuition of a massive world model, but you are refusing to pay the real-time compute tax to run it.
Which is the dream.
Yeah, the optimization strategy here addresses the fundamental bottleneck in scaling generalist robotic policies.
Well, let's back up to that fundamental bottleneck, actually, because we need to define the tension this paper is trying to resolve. We see this massive trend of smashing vision language models together with world models.
Right, the VLA trend.
Yeah. In a perfect world, why do we even want those two architectures sharing the same brain?
Well, because they solve two completely different halves of the robotics problem. Like an LLM, or a vision language model, is a semantic engine.
Right.
It looks at an image and understands that a mug holds liquid, or an apple is a fruit, and that glass shatters.
It has that incredible common sense reasoning sweep from the internet.
Exactly. But it has absolutely no idea how the apple actually rolls off the table, or the specific parabolic arc of the water pouring out of the mug.
It knows what things are, but not the physics of how they move through space.
Which is why we need video generation models or world models. A model like Sora or WAN 2.2 has internalized intuitive physics. It knows how lighting changes when an object moves, how friction works, how gravity pulls.
So, the obvious engineering move is to combine them. Give the robot the LLM's semantic brain and the video model's physical intuition.
Right. But the paper explicitly states this causes three massive issues in practice. The first is what they call the lobotomy problem.
Or semantic drift, yeah. I want to spend a minute here because the mechanism behind why the model forgets things is fascinating.
Oh, really is.
When you add heavy generation and action objectives on top of a VLM, researchers usually they stop training it on large-scale VQA, with the vision question answering stuff.
Yeah, usually because they simply don't have the compute budget to keep doing both. Training continuous motor control and future pixel prediction is intensely demanding.
Yeah. But stopping that VQA training is fatal. The network starts to literally overwrite its semantic weights. It is like trying to save a massive 4K movie file onto a hard drive that is already completely full of your text documents.
That is a perfect analogy, actually.
Because pixel reconstruction is such an incredibly dense, heavy loss objective, the network just frantically searches for available parameter space to minimize that loss.
Right. It needs room.
Yeah, so it ends up literally overwriting its understanding of what an apple is just to find the capacity to render the exact red RGB pixels of the apple falling. The gradients are fighting for the exact same parameters.
And that optimization interference is the core issue. You have heterogeneous objectives fighting a tug of war.
Pulling it apart.
Exactly.
Yeah.
You are trying to optimize for regressing visual latents, calculating flow matching for physical actions, and standard language modeling, all at the exact same time. The network just gets pulled in way too many directions.
Right.
And honestly, worst of all, in most unified architectures, the visual prediction modules are trained completely from scratch.
Which is just wild when you think about it. We have these massive pre-trained video generators sitting right there. Why are researchers forcing their robot policies to relearn how light and gravity work from zero?
Well, because plugging a billion parameter video generation model directly into a robot policy typically destroys the real-time latency you need to actually operate a robot arm.
Right.
You can't wait 5 seconds for a diffusion model to render the next frame when your robot is trying to, catch a moving object.
Yeah, it would just drop it. And this is where InternVLA-A1.5 introduces their primary architectural breakthrough. They recast future prediction as a latent querying problem. They cheat the pixel tax.
They absolutely do.
Instead of forcing the model to perfectly predict the exact RGB values of a future frame, they use a small set of latent foresight queries.
Right, and these are basically just learnable tokens. Think of them as a highly compressed antenna. They attend to the shared multimodal context.
So like the current image the robot is looking at, the text instruction it was given, its current joint states.
Exactly. Their entire job is to read out the task-relevant future and condense it into a very compact latent code.
Just a mathematical representation of the future physics without rendering a single pixel.
Right.
But I'm stuck on something here. If we aren't generating images, how are we supervising these tokens?
That is the trick.
Because the paper says they use the flow matching objective from 1.2.2.
Yeah.
And I've seen flow matching replacing diffusion in a lot of recent papers, but how does that objective actually train these tiny foresight tokens if everything stays in latent space?
So to understand how they supervise the tokens, we really need to look at what 1.2.2 is doing during training. Flow matching is essentially about finding the optimal, most direct path from pure noise to structured data.
Okay.
Think of it like trying to map the most efficient river current between a puddle of random static and a crystal clear video of the future. The model calculates a vector field, a target velocity, that represents the exact speed and direction needed to push those static pixels into reality.
Okay, so during training, InternVLA takes a ground truth video of what actually happens next. It encodes that into a latent representation. Then it takes pure noise, and 1.2.2 calculates the flow.
Right, the target velocity to turn that noise into the true future.
Yes, okay.
And here's the brilliant part. The compact latent code produced by our foresight tokens acts as the conditioning input for that flow matching process.
Oh, interesting.
So when the loss is calculated, when the network looks at how far off its predicted velocity was from the true target velocity, they backpropagate that error. But they freeze all the 1.2.2 parameters.
Wait, they freeze the whole video model?
Entirely. The error signal skips the massive video model entirely and flows straight back into those tiny foresight tokens.
Wow. Okay, so the video model acts purely as a teacher grading a test. It doesn't actually learn anything new.
Not a thing.
The foresight tokens are the students desperately updating their internal weights until they provide the exact right conditioning signal that makes the teacher's physics engine happy.
That is exactly the dynamic. And because 1.2.2 is frozen, it preserves all of its pre-trained knowledge about physical dynamics, lighting, object permanence.
It effectively distills that massive spatiotemporal understanding down into the foresight tokens.
Exactly.
Which answers my next question, actually, because if we hook a policy up to a massive 1.2.2 video generation model, how on earth is this thing running on a robot in real time? I mean, a robot arm needs commands at 20 hertz or higher.
Well, you drop the video branch entirely at inference. You literally just throw it away.
You just delete it from the loop.
Yeah, once the policy is trained, those foresight tokens have already absorbed the teacher's physical intuition. When you deploy the robot in the real world, it only runs the QuIN-VLM and a lightweight expert module.
So you get the real-time execution speeds necessary for motor control, but the policy making the decisions is permanently imbued with the physics priors of a world model.
It's an incredibly elegant bypass. We solve the dynamics problem without paying the inference tax.
But I want to push back on the architecture for a second, because we still haven't actually solved the lobotomy problem. I mean, if the video model is dropped, the physical motor commands still have to be generated somehow, right?
The robot still has to move.
And historically, if you bolt a separate neural net, like an action head, onto the side of an LLM to generate continuous joint movements, that is exactly what ruins the semantic brain.
Yeah, a bolted-on action head forces the network to learn a completely separate output space, which drags the gradients away from the language representations. But InternVLA-A1.5 avoids this by rethinking the prompt design itself.
Okay, how?
They don't bolt on a separate head at all. They append the discrete action tokens directly to the VLM's existing vocabulary.
Wait, so the action tokens share the exact same embedding table and output projection as standard language tokens?
They do.
So we're basically tricking the LLM into speaking motor control as if it were just a new dialect of English.
Essentially, yes. They cast the robot's states, its control modes, and its actions directly into the native chat template of the QuIN-VLM.
Oh, wow.
You aren't forcing the model to learn an alien architecture. You're just teaching it a few new vocabulary words that happen to correspond to physical coordinates.
Okay, but how does a discrete vocabulary token turn into the continuous fluid motion of a robot arm? Because the paper mentions the unified expert uses Euler integration with 1 over k steps. If it's just speaking discrete words, where does the continuous flow come from?
This is where the unified expert module comes in. While the VLM outputs discrete tokens to plan the high-level action, the lightweight unified expert takes those representations and formulates the actual motor control as a continuous flow matching problem as well.
Okay, flow matching again.
Right. Instead of just jumping from state A to state B, Euler integration breaks the trajectory down into tiny iterative steps, those case steps you mentioned. Starting from random noise, the expert iteratively refines the predicted action chunk.
So it takes a small step along the calculated vector field, reevaluates, and takes another step.
Until it resolves into a smooth, continuous motor command, yeah.
And because this is all still tied to that shared embedding space and formatted as a standard chat dialogue, the entire system is supervised under a single cross-entropy loss.
Which is the secret to the training stability. I mean, if you are an engineer listening to this, you have probably felt the pain of tuning loss weights.
Oh, for sure. Trying to balance a language loss of 0.1 against an action loss of 5.0.
It's awful.
Yeah.
But InternVLA-A1.5 just removes that friction. By unifying the vocabulary and maintaining the VQA training simultaneously, the semantic brain remains completely intact.
The spatial grounding and instruction following capabilities that Qwen 3.5 already had are entirely protected.
Exactly.
Okay, I see the architectural brilliance here. We have a preserved semantic brain and latent foresight tokens stealing physics from a frozen video model.
Right.
But I have a major concern about the data. Because if this model is so good at preserving its semantic knowledge and it's being heavily supervised by synthetic physical dynamics, what stops it from completely overfitting to a simulation?
That is a very real issue.
I mean, a real-world robot has to deal with variable friction, weird lighting, chaotic human environments. Where does the messy real-world data actually come in?
It is a massive challenge because the data distribution in embodied AI is incredibly skewed right now. InternVLA-A1.5 was pre-trained on 1.2 million robot episodes and 3 million multimodal samples.
Which sounds like a lot.
It is, but look at the breakdown. You have synthetic datasets like InternData-A1, which boasts an astounding 396 million frames of clean, simulated physics.
Wow.
On the other hand, vital real-world datasets like RoboMind 1.0 only have about 5 million frames.
Right, so if you just toss all of that into a bucket and do standard proportional sampling, the synthetic data will just completely drown out the real world. The model will assume gravity is perfect and friction is a constant.
Exactly. So to prevent the simulation data from bullying the real-world data out of the batch, the researchers utilized a two-level group sampling scheme combined with what they call remix weights.
Remix weights, so they didn't leave the sampling to chance.
Not at all. Each source dataset forms a group, and within that group, sub-datasets are drawn proportionally. But the crucial step is how they explicitly weighted the groups against each other.
So they manually put their sum on the scale for the smaller datasets?
They did. They explicitly upweighted sources like Droid, Galaxia, and RoboMind 1.0. Even though their raw frame count is a tiny fraction of the synthetic pool, these datasets provide vital embodiment diversity.
Different robot arms, different camera angles, messy real-world kitchens and labs.
Yeah. By forcing the model to pay disproportionate attention to these smaller datasets during training, they ensure the policy learns to generalize to unstructured environments.
Well, let's see if that remix strategy actually paid off. I want to look at the benchmarks, because it's easy to build an elegant architecture that completely fails when the rubber actually meets the road.
Oh, it definitely paid off. Across all 6 simulation benchmarks they tested, InternVLA-A1.5 achieves the highest overall results.
Let's frame what those numbers actually mean for performance, though, because the margins are staggering. Take SimplerEnv, specifically the WidowX robot arm evaluation.
Right, a very standard benchmark.
The baseline models, like PyO, were failing constantly, scoring around a 27.1% success rate. Even PyO 0.5 only hit 57.1%.
Yeah, pretty rough.
But InternVLA A1.5 jumped to an 80.8% average success rate. That isn't an incremental bump. That is the difference between a robot that shatters your coffee cup 3 times a week and a robot you actually trust in your kitchen.
The spatial reasoning improvements are just as severe. On Libero, which tests object goal generalization, it hits a 98.9% success rate.
Wow, 98.9%.
Yeah. Now, but if we really want to prove that the lobotomy problem was solved, that the semantic brain is truly intact, we have to look at the real-world out-of-distribution tests.
Right, the compositional generalization. This is the ultimate test for these models, because when you train a robot to put a blue block in a left box and an orange block in a right box, the fear is always that the neural net just memorized those exact joint trajectories.
Right, that it didn't actually learn what blue means or what left means.
So to test this, they ran a real-world experiment on the MoveTubes task. They asked the robot to perform an entirely unseen combination. They instructed it to move orange to hold 24.
And the model had never seen that specific combination of color and destination in its training data.
Never. So if it had just memorized trajectories, it would fail completely. It would either reach for the wrong color or put it in a hole it had previously associated with the orange tube.
But it didn't. InternVLA-A1.5 scored an 83.3% success rate on that held-out task.
That is the smoking gun right there. It proves the VLM actually understands what the objects are and how they move, and can combine those concepts on the fly in physical space.
And we know for a fact that the Latent Foresight tokens are responsible for modeling that physical interaction because of the ablation study they ran.
Oh, the domino benchmark ablation.
Yes. Domino heavily tests dynamic object interactions, predicting what happens when two objects collide or push against each other. When the researchers stripped the Foresight tokens out of the architecture, the success rate on that benchmark dropped from 27.7% down to 23.8%.
So the baseline drops significantly the moment you take away its ability to query that frozen physics engine.
Right.
Those tiny tokens are doing an immense amount of heavy lifting.
They really are. It forces us to rethink how we extract knowledge from foundation models entirely. You let the frozen video model act as the physics engine, the language model act as the semantic engine, and the latent tokens act as the incredibly efficient bridge between them.
So, synthesizing this all together, the era of training pixel-level video generators from scratch for robot control might just be over?
I think it is, yeah.
I mean, why pay the massive compute cost to render a 4K video frame of a robot moving a block when no human is ever going to watch that video? By condensing that physical foresight into a handful of latent tokens querying a frozen world model, you get the physics priors you need at a fraction of the cost.
And you combine that with a native chat template that protects your VLM from optimization interference. And you have a blueprint for generalizable real-time robotics.
The implications for scaling are immediate. You are no longer bottlenecked by the pixel generation tax.
Exactly.
But the authors note a limitation that I actually think hints at the next major breakthrough. Right now, this foresight supervision only spans a very short horizon, just one action chunk. It is predicting a fraction of a second into the future.
Right, it is very immediate.
But think about the logical conclusion of this architecture. If a few latent tokens can accurately capture immediate physics, what happens when we start chaining these latent tokens together for long horizon planning?
You were talking about recursive latent imagination.
Exactly. Could future versions of InternVLA daydream an entire sequence of complex tasks purely in latent space? Imagine a robot planning an entire day's work in milliseconds, predicting collisions, tool uses, and cascading physics interactions over hours of operation without ever rendering a single video frame.
Just manipulating dense little nuggets of future possibility in its latent space.
That is something for you to chew on as you design your next architecture. Thank you for joining us to unpack this paper. Stay up to date with us here at AI Paper Slop, and we'll see you next time.